Today we will start an important topic. This is the notion of modules. It's a unifying notion. It captures many different things that we have seen under one single umbrella. So let me give you the definition first. So what's a module? So to define a module, what I need is a ring. So here's the definition. Let R be a ring. So not necessarily commutative. A left R module remember we have encountered this notion of left and right ideals before. So when a ring is not commutative, one often has to distinguish between these two notions. So in this case, we will call this a left R module. That's what I'm going to define. Is the following: is an abelian group. First, it is an abelian group. So let me call it M, and let's denote the group operation by plus, so it's commutative, together with a map. Okay, so this map is from R cross M to M. Okay, so we write, given an element alpha in R and X in M, let's denote the image of this map by alpha dot X. Okay, satisfying the following axioms. So satisfying the following axioms. Okay, axiom number 1 says, when I take alpha and combine it with x plus y, alpha dot x plus y is the same as alpha dot x plus alpha dot y, and this holds for all alpha in R and for all x and y coming from M. It's property 1. Property 2 says, if I look at two elements of the ring, alpha and beta, then alpha plus beta dot x is the same as for all x in M. So these are sorts of some sort of distributive properties. Property 3 says, if I multiply two elements, alpha and beta of the ring, so their product is again an element of the ring, I multiply them and then act on x, then this is the same as alpha dot beta dot x. This is for all alpha beta in the ring R and for all x coming from M. And finally, property 4 is the identity. If I take the identity element, the multiplicative identity of the ring, and look at that dot x, then the answer is x, and this is true for all x in M. Okay, so those are the 4 axioms which this map R cross M to M is supposed to satisfy. Okay, now this set R, the elements of R. So let me just say, this is supposed to remind you of something that you must have seen before. So elements of R are sometimes called scalars. Okay, and this map from R cross M to M is sometimes called scalar multiplication. Okay, so of course that should ring a bell. So observe that this is in fact exactly, it looks a lot like the definition of a vector space, and in fact that will be our first example. So immediately one observes that this definition is really motivated from the definition of a vector space. Okay, so example, let's take R to be a field. So now let me call it K. So K could be the field of real numbers, complex numbers, finite fields, whatever. So I take a field K and let M now denote a vector space over this field. Then observe that these axioms are exactly what it means for M to be a vector space. Okay, so then observe M is an R module. So the axioms of a module are exactly the axioms of a vector space when R is a field. Okay, so that's our primary example. Now here's a small remark. So I defined left modules instead of right modules. So let me also tell you how you would define a right module. So a right module, a right R module M is again an abelian group. Okay, so let's say with a plus operation, satisfying, well, almost the same axioms as before. So axioms 1, 2, 4, but not 3, and instead of 3 they have an axiom which is now called 3 prime. So let's just go back and look at what axiom 3 said. Alpha beta acting on x or dot x, the scalar multiplication should be alpha dot beta dot x. Now 3 dash is the following: if I take the product of two scalars alpha and beta and act it on x, then I demand that the answer should be beta acting on alpha dot x. Okay, so this is what it means for a module to be a right module rather than a left module, that the sort of the order of alpha and beta is interchanged. Okay, now observe that if the ring is commutative, so if R is a commutative ring, then, well, these two notions are really the same. If R is commutative, then observe that the notions of left and right modules coincide. Okay, in other words, a left module over R would automatically be a right module, and a right module would automatically be a left module. Okay, that map R cross M to M actually satisfies both 3 and 3 dash if R is a commutative ring. Okay, that's what we mean. In other words, the map from R cross M to M satisfies the axiom 3 if and only if it satisfies the axiom 3 dash. Okay, and you can check this quickly. All you have to do is just take, instead of alpha beta here, I can replace alpha beta by the product beta alpha. It's the same thing because R is commutative, and then observe that axiom 3 dash would just reduce to axiom 3. Okay, so write out a formal proof of this fact. Okay, so far we have defined the notion of a module and realized that it's actually nothing but a vector space in disguise. You can sometimes say a module is like a vector space over an arbitrary ring rather than over a field. Okay. Okay, now a field, remember, is a very special kind of a ring. A field has two important properties. Number one, it's a commutative ring. Okay, commutative ring. And the second important property is that all non-zero elements have multiplicative inverses. All non-zero elements have multiplicative inverses, right? So these are the two important properties that a field possesses. A general ring, of course, doesn't have either of these properties. A typical ring can be non-commutative, and even if it's commutative, no reason for it to have inverses, right? So you've already seen many examples of rings of both kinds. So of course the theory of modules over an arbitrary ring is much richer. Okay, so the ring doesn't necessarily have to have these special properties, and so the class of examples, the kinds of properties you get, and so on, everything is now a much richer setting. Okay, so let's look at the first example of a module which is not over a field. Okay, in other words, let's look for a module which is not a vector space. So here's example over a non-field, let's take R to be the ring of integers. Okay. So let's ask, what is a module over the ring of integers mean? Well, if I take, so let M be a Z module, let M be a Z module. So let's try and see what that means. Okay, so first property, recall, that means that M is an abelian group, it's got an addition operation, and with respect to that, it is an abelian group. And the second part of the definition said that there should exist a map. So there exists a map from Z cross M to M. This is the scalar multiplication map, if you will, which is, if I take a pair n comma x, maps it to what we call n dot x. This is the scalar multiplication of x by the integer n. So n is in, okay, satisfying various axioms, right? So let's look at such that certain axioms hold. 1 through 4 hold. Okay. Now these axioms actually impose rather severe restrictions on what this map can actually be. Okay. For example, let's look at axiom 4. So here's axiom 4, which says, if I take the multiplicative identity of my ring, which in this case is the number 1, and I scalar multiply it with any element x, then I should get x. Okay. So I know this already by axiom 4, that 1 dot x is x. Okay. Now we can quickly find out many other things from this. Let's look at 0 dot x. Okay, what do you get if you multiply x by a 0? In fact, this is true in arbitrary modules. So what is this? Well, as always, this is, so you must have seen this calculation many times also in previous courses. If I try to compute 0 dot x, I can write it as 0 plus 0 dot x, and then use the second axiom, axiom 2, which is sort of a distributivity axiom, which says this is nothing but 0 dot x plus 0 dot x. So 0 dot x is the same as 0 dot x plus 0 dot x in the module M, and of course the module M is an abelian group. So I conclude, so this is what I conclude, and of course in this abelian group I can cancel these two elements. In other words, I can add the inverse of this to both sides and thereby conclude that 0 dot x must just be the element 0 of my abelian group M. Okay, so I found out two things already just from the axioms. 1 dot x is x, 0 dot x is 0, and let's look at a few other ones. Let's ask, what is minus 1 dot x? So what is minus 1 dot x? So observe, so what is minus 1 really? So 0 dot x is 0, but I can also write 0 dot x as, right, so 0 is just nothing but what I get when I add 1 with minus 1, and now again I use my axiom 2. This says this is 1 dot x plus minus 1 dot x. Okay. Now of course I've already concluded that 1 dot x is x, so here's my conclusion, that x plus minus 1 dot x is just the element 0 of my abelian group. So this is what I conclude finally. Okay, so this holds. So all this is now an equation in M. Remember, both sides of this equation are elements of my abelian group M. Okay, so what does this mean? It just means that this element which I am trying to find, minus 1 into x, minus 1 dot x. So here's my conclusion, minus 1 dot x is therefore the additive inverse of x. In other words, that's the element minus x. Okay, so this is just the additive inverse of x. Okay, so I've concluded that minus 1 times x is just the element minus x. Now one can sort of keep going. You can already imagine where this is heading. So I can compute, say, 2 plus x, it's just 1 plus 1 dot x. So 2 plus x is nothing but 1 dot x plus 1 dot x. So it's just what I get when I add x with itself twice. More generally, if I try to take a positive number n and try to, so I have to use distributivity repeatedly, but you can check that this is what I get. It's just x plus x plus x n times. Okay, so this is if n is a positive integer, and from here I can also figure out what I get when I multiply by a negative number. So this, for example, so here's a quick way to do this. So I can think of n as minus n as just minus 1 times n. So this is just the usual multiplication in the integers. This is just minus 1 into n, the product, this scalar multiplication with x, and this by axiom 3 is just minus 1 acting on n dot x, and of course we have already said n dot x is nothing but the element x plus x n times. Okay, so this is the element in M, and now we have already done this, right? If I take any element of my module and I scalar multiply it with minus 1, it just gives me the additive inverse of that element. So this is just minus of the, so it's the additive inverse of x plus x n times. Okay, so what does that mean? What have we managed to do so far? Just starting with the axioms, okay, we never used anything more. We have figured out that there is really only one possible map that you can define which satisfies these axioms. Okay, the map z cross m to m is almost forced in some sense, right? N dot x, I have figured out, has to be one of these. If n is a positive number, then n dot x is just add x with itself n times. If n is or instead of n I take minus n, a negative number, then that answer is just minus of x added with itself n times. Okay, so this is sort of, this just tells you that this is all forced in some sense. It's forced by the axioms. So so let's sort of forget this bit of the calculation and maybe just go ahead and define, given any abelian group, you can make it into a Z module as follows. So that's really the conclusion here. Given an abelian group M, it can be made into a Z module via the definition n dot x is just either x plus x n times, this is if n is positive, or it's minus of this if n is negative. Okay, now this has to be mod n times, or if n is 0, then of course the answer is 0. Okay, so you have to check. So now I am giving you a definition. Take any abelian group and you define the scalar multiplication by z in this manner, then this becomes a Z module. Okay, it's a check that it satisfies all the axioms. Okay, exercise, check axioms 1 through 4. Okay, and sort of conversely, what we just showed is that if I have a Z module, then in a sense that Z module is more or less the same data as an abelian group. Okay, I don't get anything extra there. The map, so if I have a module over Z, of course I have an abelian group, but conceivably I could define some strange scalar multiplication map. There are many different ways of defining scalar multiplication by Z, right? But what we have just shown is that no, that's not possible. There is only one scalar multiplication map that you can define which satisfies all the axioms that you need to satisfy. Okay, so in a sense it says that talking about a Z module is the same as, the data of a Z module is really the same as the data of an abelian group. There is no extra data there. Okay, so these two notions are actually identical. Okay, so what we have just shown is that Z modules are really the same. So it's a slightly loose statement because what same means is in the sense of our discussion. Z modules are the same as abelian groups. Okay, in other words, given a Z module, I can look at the underlying abelian group and given any abelian group, I can make it into a Z module in this manner. Okay, so that's sort of our first example of a module which is not a vector space. Okay, so next time we will look at another example which is slightly more non-trivial than this one.